All right, welcome to Chapter 4, Coordinate Systems. Coordinate systems are by far one of the most important facets of doing GIS. While the program is very smart as to how it handles coordinate systems, if you don't understand what's going on, it's very difficult to fix issues or make sure that all of your data can overlay itself and so it's all in the right spot. And you could have all the cool data in the world, but if you can't get it to overlay, having that data doesn't mean anything. So this particular chapter is one of the most important, in my opinion, and I really stress it to my students to understand not only how to use the tools for handling coordinate systems, but understand what's going on. And trust me, at least we don't have to do any math. That's the main thing. But definitely want to understand this by the end of the chapter. All right, so we live on this blue planet called Earth, right? And so the program needs to understand where on Earth the data that you have sits. Okay, and so in the background, the data has the XY coordinate system, sometimes the Z as well, to locate whether it be vector or raster data somewhere on Earth. Once it knows that, once it understands where it's supposed to be placed on Earth, the data is said to be georeference. So this is hugely important because if you go out in the field and take data, in itself, it's not always easy to just bring it into GIS. There's a few steps you have to take in order to get it to that point. Now, we discussed a little bit back in chapter 1 the fact that vectors have a mathematical formula, so to speak, here that gives it its x and y values, and the program knows where to place the vertices in order to place a point, a line, or a polygon. And then in raster world, we know the upper left coordinates, the XY coordinate, and then the number of columns, the number of rows, and how wide those columns and rows are, whether it be 30-meter DEM or 10 meters. We understand the number of columns, and then it just basically calculates it in this direction. All right, and then it can place it somewhere on Earth. However, there are those times when you don't have that ability. You don't have the perfect place where to put it. You might have the Latin lawn, but just the Latin lawn by itself, the program doesn't still know where to put it. So there's some concepts that you have to sort of wrap your head around in order for it to get to that point where you could put raw data, only knowing the latitude and longitude, into GIS. So you can have different coordinate systems. You could set up manual ones, customary ones, local arbitrary ones, like a building site, for example. However, there's lots of standard ones that are being used throughout the world, but for our purposes, mostly North America, that make doing this much easier. There's only about 4 of them that you really have to understand for sort of the area of the world we live in, and then some other more specific ones for, let's say, Wisconsin, and we'll get into those as we go along. So there are some standard coordinate systems, okay? So if you look at this little itty bitty USGS map here, it could be that point on that map can be representative in let's say 3 ways. The first one here is Latin lawn, right? I'm going to try to type here. Yeah, that's not good. Anyway, so that's Latin lawn. That's what we know from our coordinate systems from Earth, with the angle being measured from the center of the Earth. Distances west are typically representatives negative numbers, north and then south are negative numbers. You could also have that same point be in some planar coordinate system in meters or some planar coordinate system in feet, depending on your needs. Neither is better or worse, it just depends on what you're working with. So you can have all 3 of these and you can switch between them utilizing some tools within GIS. Now, one of the things that you have to understand, and I'm going to repeat this several times throughout this chapter, is you do not want to do any analysis in Latin lawn. And we'll get more into that as we go. So your data for your projects should be in one of these 2 here, always. I do check for that. You never ever want to do analysis in Latin lawn. We'll get more into that in a bit. So there's 2 types of coordinate systems, what's considered unprojected or geographic, and projected. Now, we live on a roundish ball, all right, that's floating through space and spinning, but it's definitely a roundish ball. It's not a flat computer screen. So those unprojected Latin lon, that's unprojected equals Latin lon. Remember that. Unprojected equals Latin lon. That's based on spherical coordinates. It's an angle from the center of the Earth, like I just mentioned. We're at about 43 degrees north, from the center, 43 degrees north, and about 87 degrees west. Okay, so that's how that's measured on a round ball. However, we do all of our mapping and analysis on a flat plane, all right, whether it be a computer screen or a map. So you have to convert those spherical coordinates to planar coordinates using a set of mathematical equations. Now, if you've ever seen the math that does that, it's very scary stuff. Luckily, everything we have to do is drop down menus. All the math's been done for us, it's all done in the background, but you still have to understand how to set it up. And it's a drop down menu, it's not complicated. You just kind of have to, dot your I's and everything, cross your T's. And that takes it from 3D coordinate system to a 2D coordinate system. And with that, there's some inherent concessions you have to make in terms of distortions. We'll get to that in a second. So just understand, unprojected is geographic coordinate systems, which is Latin lon. So unprojected equals Latin lon. Projected is planar coordinate systems. So every piece of data that comes into GIS has to have a, uh, what's called a label, a coordinate system label. All right. So when you look at where the data is sitting in your map and you roll your mouse around, you can see the projection coordinate system as you move that around. So if you see these big weird numbers like this, that means it's already been projected onto a two-dimensional plane, and you're never going to know what those numbers are. You don't have to memorize any of that. You just know that you have to understand whether or not you're in feet or meters. That helps. But just know that you're already in two dimensions. Whereas this one down here, those numbers should look semi-recognizable in the sense that you have negative y values and positive x values. There you go. You got Latin lon, right? So that's unprojected because it's still in spherical coordinates. And while you can place them on a map that way, that's about as far as you go with that. In order to do anything further, you have to convert them to two-dimensional planar system. So I'm not going to go into gory detail about this. I hope all of you know this already. Latitude and longitude is measured from the angles east and west from um, north or south or east and west from the center of the earth. Again, you should all know this by now, I hope. If not, look it up online real quick. I'm not going to spend a lot of time on this because one of the oddities is we already know this, hopefully, from previous courses, but we don't spend a lot of time in this because, again, our first step is when we get data into our GIS, we want to convert it right away to two-dimensional planar coordinate system anyway, so it's not actually being stored in Latin lon very long. So one of the problems is that there's not very much precision in GCS. Now you see the acronym GCS. That stands for Geographic Coordinate System. Geographic Coordinate System, or GCS, equals Latin lon, which is unprojected. So GCS equals Latin lon, which is unprojected. You should probably know that. So that's stored in degrees, and a degree at the equator is about 110 kilometers. You can see that there. And so the problem is that you have in order for better accuracy, because the math changes, excuse me, the math changes as you go north or south with parallels of latitude. They get closer together. The math changes. So your accuracy is not very good in GCS already, but there's more to that story, and I'll explain that as we go. So the other part of this is, I mentioned earlier, we live on a roundish ball, right? It's not a perfect sphere, it's a spheroid. So the spheroid is a slightly flattened or ellipsoid shape, right? But smaller, it has a smaller north-south axis. Well, the Earth is also not a perfectly smooth sphere, right? We have mountains, we have valleys, we have ocean. It is an irregularly shaped object, okay? So a geoid is a surface modeled from gravity differences to get to its closest shape because you're going to have higher gravity in mountain ranges, lower gravity in basins, things like that. So but it's too complicated for mapping. Now, when you combine the two together, when you combine the spheroid, all right, with the geoid, what you get is called a datum. And what you try to do is get the best fit between the two for the area that you're trying to map. Okay, so you can see here they line up pretty well right here. Well, here, there's a big gap there. So I would not use that datum to map in this area, but I would up here. Okay, so we have to take into account the irregular shape spheroid, the flattening of the Earth, along with the irregularly shaped surface, combine the two to find the best fit for the area of the world that we're trying to map. And that's called a datum. A datum is an approximation for Earth shape used for mapping. It shifts the ellipsoid relative to the geoid to achieve the best fit between the two. Okay, so a local datum, which is what most of the data we use is, optimizes that shift for a particular location. Okay, um, and then they kind of survey them again and again to get better accuracy. So what you'll hear me say, and I'll talk about these a bit more, is something like the North American datum of 1987, or excuse me, 1983. All right. So, or NAD 83 for short. NAD is North American datum. That's a datum that's used obviously in North America, but would not fit for South America or Europe because that fit is not going to be as good somewhere else on Earth because it's been shifted to fit specifically in North America. There are also geocentric or world-centered datums that optimize the fit for the whole world. And that's kind of where GIS is going in terms of a lot of the datums. Because we have such high accuracy telemetry from satellite data, you can get world-centric datums that are pretty much good everywhere on Earth. And that's kind of where it's going forward. So these are the four that you're going to use pretty much throughout this class. Okay, we don't do much GIS outside the confines of North America at all in this course. In fact, I make it a requirement or a restriction, I guess, if you will. You cannot do any type of final project outside of the lower 48. I even exclude Alaska and Hawaii because of both uh, there's not a lot of population dense centers there and the coordinate systems, and it's just we keep it to the lower 48. There's plenty of opportunities in the lower 48 states. All right, so we have four main datums. You have North American datum 1927, which you'll also hear me say NAD 1927 or even shorter, NAD 27, because who wants to talk more than you have to. You have NAD 83, which is an updated version from 1983. This is by far the most current one and most popular. Okay. And then they updated that a little bit more with NAD 83 HARN, which is the high accuracy regional network. Okay. And then finally, you have the first World Geodetic Survey in 1984, or WGS 84, which is the geocentric datum for the entire Earth based on, again, satellite telemetry, and it seems to be the default for most GPS units. Now, of all of these, this one by far is the most used right now. Okay, you're going to see most data in NAD 83. Sometimes NAD 83 HARN, sometimes NAD 27. I make no restrictions on these. I don't care which one you would use for your final project, as long as every single piece of data that you turn into me has the same projection. There can't be one in this and one in that and maybe some in Latin lawn. You do get graded on that. So you have to have everything in one projection. And it's not hard to do that once I show you the tricks for setting stuff like that up. But NAD83 by far is the most popular. And, when choosing data that's, coming in raw, so to speak, NAD83 is always a good starting point. Now, when you choose a datum, usually you'll see lots of different options. So you can see in this box, those are all NAD83, and then you got a bunch of stuff in a parentheses. Pretty much always, at least to start with, use the very basic one first. These all these other ones, including the Harn to some extent, are very specialized versions and are usually used for very, very specific things. So when in doubt, use the most basic one, NAD27, NAD83, WGS84, nothing else. Just real simple, leave it like that. Don't mess around with anything in parentheses. I don't even know what half of this stuff is, to be perfectly honest with you. So, because again, they were probably used for a very specific purpose. Stick with the very basic ones. Now, what happens if I have one set of data in NAD27 and I have another set of data in NAD83? Well, I just mentioned in the previous slide, a couple slides ago, you're required to have all your data in one projection. You can do this in GIS fairly simply. And that's called a datum transformation, where you're going from NAD27 to NAD83. And technically, it's a two-step process, although they've made it much easier, and it's a one-step drop-down now, of course. But you have to be careful with how you do it, and B, how many times you do it, because any types of errors that might be introduced into the transformation can compound themselves. I had this happen to me when I was first learning how to do this. I screwed up so much data because nobody told me how to do this stuff. So once I finally figured it out, I do it the same exact way every single time, and I'm going to explain to you guys how to do it. That way you never screw up data like I did. Um, as a side note, in years past, many years ago, I knew people with GIS certificates that still didn't know how to do transformations and understand projections. It's one of those things that you just have to nail down and then you're good to go. All right. So conversions should only be done when necessary. Now, for our purposes in our class, you're not going to hurt anything because if you're working at the county level, going from NAD 27 to NAD 83 or NAD 83 Harn isn't a big deal. So we're good in this class, but you do want to pay attention to how much you're doing this to any given data set. You don't want to keep changing it, change it back, and that kind of thing can compound any issues that might be inherent in the data itself. All right, so if you get this transformation warning, it alerts you when data is set up in different datum. So what do I mean by that? When you add data to a map, the map assumes that coordinate system. And that's a big rule. That's something you want to know. It's I call it one of the cardinal rules of GIS. If I add a piece of data in NAD27 to my map, the coordinate system my map is going to use is now NAD27. Anything I add after that is going to be projected in the background on the fly, which we'll talk about in a minute. It'll be projected on the fly to NAD27. So if I add something in NAD83, it's going to project it in the background to NAD27 and give me this warning. It's saying, hey, you're adding data that's in a different datum than what the map is already in. Okay, now the beauty is that the program is very good at figuring this stuff out in the background. Okay, so you want to make sure that you understand what you're trying to do and that it's okay to do it. Like I said, for the purposes of our class, if you get this warning, you could pretty much ignore it, but don't, you know, you can ignore it most of the time. It's fine. Now, we don't do this in this class, although we probably should, but if you're doing GPS measurements and then you're out in the field with a GPS unit, you have to make sure that you understand what the datum is the unit is taking your data points in. And like I mentioned earlier, um, a lot of GPS units are sort of set to default to WGS84, which makes sense because the satellites that they're pulling their data from are also running in WGS84. So you have to make sure that you understand what datum you're using when you're collecting your points. All right. Because if you don't, you're going to try to use the points and you could create issues later on. Now, getting back to going from 3D to 2D, what is a projection? A projection is essentially unrolling the Earth onto a flat sheet of paper, right? It's a mathematical conversion to take Earth from a round ball to a flat plane. All right. And the shape is defined by the datum or the GCS. So in our case, most of the time we're working in North America, we're going to use NAD 83, NAD 27, whatever. So the choice is definitely going to be dictated by the area of your interest for your map. Now, you can have different datums on different maps, or excuse me, on the same map. However, sometimes what you'll notice is things just don't line up right. Now, you can see in this image here, you have roads, all right? They were both in UTM coordinate system, which I'll talk about in a bit. But one is in NAD 27 and one is in NAD 83. So the photos in NAD 27 and the images, or excuse me, the vectors roads are NAD 83. And you can see there can be a very big difference between the two. So sometimes it's definitely worth converting data from one to the other to ensure that there's a better fit. That obviously doesn't fit right. So there's three kinds of projections, and I'm not going to dwell on these too much. The book does a pretty good job of covering this. So you have cylindrical, conic, and azimuthal or planar. Um, and when you're doing this at the scale of your projects, none of this is applicable. You're working at, let's say, the county level, so there's zero distortion. But when you're working at small scales that cover large areas, you have to take into account what the map is going to be used for. And there are concessions that need to be made. Do you want to keep it equal area, um, equal, conformal, or keep your shapes, true distances, true direction, things like that. So within the parameters of these coordinate systems, you have several things, including what central meridian the map is based on. So, for example, if I'm doing Milwaukee County, I would use minus 87 maybe, or the standard parallels, which are everything in between those two parallels has very minimal distortion. So sometimes you just have to worry about that kind of stuff, the latitude of origin. And then the final two are false easting and false northing. And you'll see this in the properties. And this is a very simple concept. Basically, if you go back to grade school math and you have a grid system, anything in the upper left quadrant here is going to have all positive values. So what false easting and false northing is they're adding a constant to either the x plane or the y plane, a big enough constant to ensure that all values in that area are positive. That way you don't have any negative latitudes or negative longitudes, although these aren't lat and lon, they're planar coordinates. It just ensures that all of your coordinates are positive. That's all that is. So some projections have standard parallels where the projection touches the ellipsoid. So a tangent projection has one standard parallel, and a secant projection has two. So basically, what that is they have their lines of no distortion. They're usually placed at the center of the tangent or at the upper or lower um, areas, just to avoid the whole purpose of this is to minimize distortion. Again, the book will explain this as well. I don't like to dwell on this too much because this is um, not really GIS, it's more cartography. And because we don't map at this scale other than in the tutorials a little bit, this isn't used very often at all. You have the central meridian is the line of longitude that's center on the map. So that's, you know, you want to, that's something you can adjust slightly to make sure that everything looks kind of nice. Nothing wrong with that. That's a good way to do that. And again, when you're dealing with small scale or large area maps, some concessions need to be made, and you have to, distortions are going to take place. So you have to understand what you need the map to preserve. So distortion is going to be either in direction, shape, area, or distance. So you can choose a projection based on try which of those you want to try to preserve, such as cylindrical with direction and shape, or conic with area and distance, or azimuthal with area. It all depends on what you're trying to do. So when you're selecting a projection, the first and foremost thing you have to consider is what area is being mapped. If I'm in Wisconsin, there's several pretty good projections I could use, both local, like sort of Wisconsin centric, or even more generic, but they'll still keep distortion to a minimum. It all depends on what you're trying to get at, or which you need to preserve, whether it be area, distance, shape, or direction. For small scale maps that cover large areas are, this is where most of this really takes precedence. So for example, cylindrical projections, if you're preserving direction and shape, conic or azimuthal for distance, distances. So for example, airline pilots, my dad was a pilot most of my childhood. He had maps that preserve direction because you don't want to be going the wrong direction when you're flying, or so it all depends on the use of the map. Now, when you start to look at large scale maps or maps that cover a small area, there's a lot more options. Okay, one of the easiest to understand, and I use it all the time because it is very handy, is what's called UTM, or Universal Transverse Mercator. So basically, they took the Earth and they subdivided it into 60 north-south um, orientated zones. So like if you look on the map right there, Milwaukee is in zone 16, and because we're in the northern hemisphere, it would be 16N. If we were somewhere down in South America, it would be 16S. All right, so the beauty of this is there's no distortion along the central meridian, and it preserves all four map properties well. So these are a good solid option when you're just trying to make a map, let's say of Dane County or Milwaukee County or something like that. A UTM zone is a super easy way to do it. Now if you're trying to look at the state level, then you might have to make a few decisions. So for example, let's take which one am I looking at here? South Carolina. South Carolina fits exactly within zone 17. However, you could see Texas covers one, two, three zones. So you would use the zone that is applicable for the area. If you're in El Paso, it would be 13. If you're in Houston, it would probably be 15, I think. Um, if you're in an area that sort of straddles both lines, like right along the line, you could probably get away with either one, or maybe use some other type of local coordinate system. Another system is called the state plane system. As you can see from the map here, Wisconsin is subdivided into three: the south, the central, and the north, because ours kind of go from north to south. Some go east to west. You can see, for example, like Alabama and Georgia, and those go east to west. All right, so some have one zone, one state plane, some have multiple. The idea is it's minimal distortions for area that fit in a single zone, which I have to giggle a little bit because you got Montana sitting there with one zone, and that's a huge state, but they do everything differently in Montana. So and you can see Alaska's got kind of a weird thing because when you start getting up into the polar regions, things start getting weird. So the idea being is these are viable options as well. So large scale maps can use state plane or UTM zones. You can define custom projections, but typically you really don't need to do that. But the main thing with doing projections, especially at the large scale, which is small areas, is being consistent. Use the same projection for everything. When you go to download data from different entities, they have a tendency to have their own specific coordinate system that they like to use. For example, the Wisconsin DNR uses Wisconsin Transverse Mercator, NAD 83 Harn, whereas Sewer Pack, which is the Southeast Wisconsin Regional Planning Commission, uses NAD 27 State Plane. So although I think they're updating that, but that up until recently that they've used vastly different coordinate systems. So when you're doing your project and if you have data from both of them, you have to make a choice. Typically what I tell students is if if 10 pieces of your data are in one coordinate system and one is in another, convert the one into the same one that the 10 is in, not the other way around. I don't care if it's an older coordinate system. I just don't want to have to uh, project 10 other pieces to fit one rather than fit one to the other 10. So just keep things consistent and make your life easier by utilizing the coordinate system that the bulk majority of your data is sitting in. So you can create custom coordinate systems. In fact, many years ago, I did an online course to learn some of this stuff where we did a custom coordinate system on the moon. So that was kind of neat. But what that means is if you know exactly what you want your center of origin to be and your standard parallels, you can tweak things. You'll do this in the tutorial a little bit with Turkey, as you see in the map there, um, to just make sure that what you're doing is really specific for the map you're trying to make. If you're really trying to center things, you can move things around. I don't typically mess with these too much just because, again, most counties fit within one zone or one state plane zone. So, but at the country level, like for example, Turkey or something like that, you might want to tweak these particular settings. Again, you'll do that in the tutorial. So here's Oregon. So Oregon is bisected by two different UTM zones here. So what you can do is you can shift the coordinate system to keep it, distinct. You can shift the meridian, which is the blue line, or shift the center of Oregon. You have some options just to move things around to ensure that you're minimizing distortion within that particular map. Here's another example. So if you start with the south, you can shift the standard parallels, and move things around. Doesn't look like they actually finished this slide, which is kind of funny. All right, so you can customize things to get better accuracy, but you do need to make sure that you need to take care to convert all your data to your chosen coordinate system. I already mentioned that. So that's something where you want to be consistent. GPS units may not be able to collect your data directly into the coordinate system you want. So once you're done collecting your data, you may have to project that data. And if you're using non-standard projections, which I don't recommend until you're really good at this stuff, you have to be very careful and document in the metadata what's going on so anybody else using that data can understand what you did. That's very important, especially for any type of customization. So the choice of coordinate systems on a map can play a major role in how the map is interpreted. For example, we're very used to seeing the Mercator projection on our flat wall maps, for example. And over the years, there's been some criticism of using that particular uh, projection because it emphasizes the countries in the Northern Hemisphere. Um, it's political, it's kind of silly, but when we see these maps, we're so used to it now that that's kind of what happens. So you have to keep the objective in mind, of course, even when choosing a projection, do you need equal distance or areas? And is navigation going to be an important where north is always up? So all of these play a role in determining what type of projection you're going to use. Again, for the purposes of this class, we're going to be doing such small area mapping down at the county level. And none of this really pertains. You can usually pick a state plane or a UTM zone, and you're going to be fine. That'll minimize the distortion, and everything will look the way it's supposed to be. Now, the coordinate system you decide to use plays a huge impact on your analysis. And I mentioned this earlier. You cannot, let me repeat, you cannot do analysis in latitude and longitude. Okay? You just can't. The math doesn't work out correctly. Okay? If the the reason being is because latitude changes in distance between latitude lines as you go towards the polar regions. So the math doesn't work out correctly. So if you're trying to do analysis in a GCS or Latin Lon, you're going to start to get some really weird wonky numbers. So it's imperative and required for this course that everything be in a two-dimensional planar coordinate system. So it's just something you have to keep in mind. It's not anything that once you start to get used to GIS that is difficult to do by any means. You just kind of have to make sure that you're always in some type of planar coordinate system if you need things like distances or areas, especially. Now, one of the things that makes ArcGIS so amazing is, if you go way back to the old days of, when they were still programming, you had to have all of your data in the same projection before you could even put it on a map. Well, that's not the case anymore. ArcGIS, starting in probably version 8, I think it was right after ArcView, um, has what's called on-the-fly projection. So if you look at the map on the left here, you can see there's 3 layers on there. One of the layers is in UTM, one is in Latin Lawn, and one is in a state plane. Yet the program is smart enough to understand, hey, I can fix this to the point where I can project them in the background without the user even knowing it and get them all to lay down on the map correctly. Okay, it does not affect anything of the original data. You're not converting, it's all done on the fly in the background, and it makes it easier, especially for you new users, to view data sets with different coordinate systems without having to go through the trouble of actually physically projecting them. However, you got to be careful with this because um, there a huge rule, and I have already mentioned this once, and this is where this comes to play. If you look at that map on the left, if you have 3 data sets, let's say I put the data set that's in UTM zone on my map first. Now my map is now in UTM. That's how the program works. It assumes the projection of the first set of data you add to your map. And then everything else after that is projected on the fly. So when I added the data that's in Latin Lawn, it projects it on the fly in the background. It doesn't even, and says, all right, here it is in UTM now. Again, it's not changing the data. It's just kind of do it in the background so you can see them put on the map together. And the same thing with the state plane. That's fine and dandy. However, if you added the Latin Lawn first, then everything's going to be projected into a GCS, and that's where bad things can happen. You do not want your data being projected on the fly back into Latin Lawn. All right, it'll look weird. Things will go, it'll work. You can see everything on the map, but you definitely don't want to do any kind of analysis whatsoever like that. So while the program is smart enough to do this, and it's a great way to, when you're first learning GIS, it's very handy. Or if you just have to make a quick and dirty map and throw some data on a map to show somebody, this is awesome and it saves a ton of time, and the program is amazing that way. But when you're doing actual research, it is imperative that you pick a coordinate system and manually project everything into that coordinate system with the tools available. And that's what's required of you for your final project. You cannot use data in various coordinate systems. You have to project this stuff all into the same coordinate system. It's not hard, it just takes a little practice. So when you're looking at the layers in your map, you can look at the coordinate systems in the map properties to examine everything that's going on there. This is actually a newer feature for ArcGIS Pro. I haven't really used this a ton myself because I have a tendency to keep track of things mentally where things are. But you can see in the picture on the left here that this particular map has several layers. You have state plane, NAD 83 state plane, GCS 1927, WGS 84, NAD 83, NAD 83 UTM zone 13N. I mean, you got a ton of different, you got like 5, 6 different coordinate systems, including one that's unknown, which we haven't gotten to quite yet, how to fix that. So all of these will show up on the map. The program's pretty smart. As long as everything's roughly in the same area, it'll put it on the map for you. But this is exactly what you don't want to do for research purposes. You want to take one, all of those should be identical. This could get really confusing because eventually you're not even going to know which coordinate system your map is in. And you have to make sure, you kind of, it's a little bit of bookkeeping and making sure that everything lines up correctly and that you're being consistent. So when you're working in GIS, there's 3 different coordinate system units, and this can kind of get confusing when you're first learning GIS. You have stored units and displayed units. Stored units are the units that are intrinsic in the data itself. So if the data is in Latin Lawn, it's Latin Lawn. If the data is in a state plane or UTM zone, it's in there. Buried in the data is the sort of the table of not Latin Lawn, but the equivalent two-dimensional coordinate system uh, um, coordinates, excuse me. So those are the stored units. You can't mess with them. In fact, you don't even see them in your attribute table unless if you run a specific tool to put them in your attribute table. So it's all handled in the background. All right. So then you have what are called the map units. So the stored units are the data itself. You can't mess with them without using the project tool or the reprojecting data. So they're sort of stuck there. Now the map units are determined by the coordinate system chosen for the map. Again, if you add data to your map in a UTM zone, for example, your map is now in UTM. However, you can, before you add any data, you can set the coordinate system of your data frame to a specific coordinate system, and everything will be projected on the fly into that. That's another way of kind of cheating the system in terms of projecting, because then you can export data and use the data frame's properties as a way to project your data. We'll get to that later. And then finally, you have what are called display units. So when you move your mouse around, you'll notice too, which I got to laugh about, this is ArcGIS Pro, but that's actually the interface for the old version. But when you move your mouse around, the you'll see in the interface of the program where your mouse sits. So the units that's where your mouse pointer is, and it'll be in the units of your coordinate system, whatever that is. However, you can actually change that um, to something more readable. So let's say we're in a two-dimensional planar system like a UTM or a state plane, right? Those numbers don't mean anything to us as humans. They don't make any sense whatsoever. However, what we can do is change those to Latin lawn, which we do understand in our brains a little bit better, and you're not changing anything other than what the mouse output looks like. So it's just a visual thing, and it can be really handy. Let's say you have some UTM data and you need to know the Latin lawn of some well locations. You could put your mouse on a well location and then kind of mentally note what this location is in Latin lawn. So again, that's just a data frame property. You can change that to anything you want. It could be miles, meters, whatever, Latin lawn. So the idea is that that's just sort of a handy thing, but it doesn't affect the data whatsoever. So I've mentioned earlier that all data has a label, and you see this label in the properties menu, but you can't like physically change it without using a project tool or a define project tool. So here you can see the planar coordinate system for the UTM zone 13, and here you can see lat and lon for a NAD 83 and GCS, geographic coordinate system. Those are called the labels, and they have to be complete in order for the data to work properly in ArcGIS. So this label is called the spatial reference, and all data has it unless if it doesn't. So there are some data when you bring it in, it'll be unknown, and you have to define it then. And we'll talk about that in a bit. So the spatial reference is the projection name, the coordinate system parameters that are stored. It's the storage units, which are, either feet, meters, or in degrees if it's lat and lon still. So those are the storage units. So it tells you next to number one what the projection is, in this case Mercator. This is the GCS it's based off of, is WGS 84. Its units are degrees here. Okay, and then all this information down here is sort of the Earth model that it's based on. The linear unit is here. So if you have a projection, your unit is going to be this linear unit. If you don't have any of this up here, then you're still in GCS and you'll only have the bottom portion. All right, now the domain part is the maximum allowable X and Y values. Now that's not that big of a deal for most purposes, but to give you an idea of what that is, if we had the entire world on a map, our maximum allowable values would be minus 80, minus 180 in the west, positive 180 in the east, all right, positive 90 at the North Pole and negative 90 at the South Pole. So that's our domain. It's the entire world. So those domains will be different depending on how big or small your map is. And then the resolution is the XY precision in which the coordinate system is based on. So the project tool allows you to go do two things, okay? It allows you to take data that's in lat and lon and give it a projection. So you're taking it from a 3D ball in lat and lon to a 2D map in planar coordinate systems. That's the first thing it does. So that's, if you bring in data and it's in lat and lon, you have to project it. You want that two-dimensional planar coordinate system so you can get things like lengths and areas that are geometrically correct. The other thing you can do with that is project one two-dimensional projection to another two-dimensional projection, and that's called reprojecting. So for example, I have sewer pack data, Southeast Wisconsin Regional Planning Commission data, and they, at least in the past, have used NAD 27 state plane. Well, most of my data is in the Wisconsin DNR, which is Wisconsin Transverse NAD 83 Harn, Wisconsin Transverse Mercator. So I have to take and combine, or excuse me, project the NAD 27 to the NAD 83 Harn, which is actually a two-step process. With it actually has two transformations. But that so you're going from NAD 27 to NAD 83, and then NAD 83 to NAD 83 Harn. Now that's all done in one drop-down menu now. In years past, in the older versions, you actually had to do this process twice, and but now they've made it much, much easier. So the idea is the project tool is the one that you will use 99.9% of the time. Let me repeat that. The project tool you will use 99.9% of the time. The other thing with this, and is very important to understand, is that when you use the project tool, you get an output. So you're taking a input and you get a brand new output with the new coordinate system. Okay, that's vastly different from the next tool I'm going to show you. So just remember that the project tool gives you a new output, and it's used to go from lat and lon, or three-dimensional coordinate system, to 2D. It is also used to reproject from one two-dimensional coordinate system to another two-dimensional coordinate system, which is often referred to as reprojecting. So sometimes what happens is you get coordinate system issues, and it could be a lot of things. Mislabeled, there's data sets that are missing or have incomplete. small discrepancies, things like that. And one of the more challenging aspects of GIS is learning how to fix these problems. Again, I have the benefit of experience and a lot of trial and error and screwing up data sets to come up with a way, the way that I've done it in the past, to really make this process foolproof. Okay, and I'll explain my process as we go along, but just know that you have the benefit of somebody who screwed up a lot of data to show you how to do it the right way right out of the gate. So hopefully you don't make those mistakes. All right, so one of the things that can happen is you can have what's called missing labels. So let's say, for example, I have a data set that looks like it should be in Latin lawn, but it says meters, or it's in meters and it says decimal degrees, or some weird thing like that. So one of the things that happens is if somebody screwed up the coordinate system projection over time, those problems compound, and that's what I was trying to explain to you. I messed up a lot of data. I just kept doing it and doing it until I thought I got it right, and I ended up just screwing it up even more. Okay, so here is the other tool. Okay, it's called the Define Projection tool. And I've always said this and I maintain this. This is one of the most dangerous tools in the toolbox. Why is that? If you look at this tool, this is the Define Projection tool, you will notice, please notice, it's very important, there is no output to this file, this tool. There is no output to this tool. If you run this tool, you are overwriting the original data. So this is why this tool can be very, very dangerous. So what I always tell my students is if you think you need to use this tool, before you run this tool, make a copy of the data first. Always make a copy first, because once you run this tool, there's no going back, so to speak. Okay. Now, let me explain how I use this tool. Okay. So, what I have done over the years is I've realized that there are ways to use this tool, and I'm sure there are maybe people that know better than I how to use this tool, but what the way I have done it has kept me going, and it's super easy for me to understand, and hopefully it'll make you understand. When you are running this tool, this is the input. Okay, that's the feature class or that you need to fix, right? The only thing that should ever be in this box, let me repeat, the only thing that should ever be in that box is NAD 27, NAD 83, or WGS 84. Not even NAD 83 Harn, NAD 27, NAD 83, or WGS 84. And you'll see that here, GCS NAT North American 1983. What you essentially are doing with this tool, the way you can think about it is kind of using an eraser. You're kind of starting from scratch. My label's all messed up. I don't know what coordinate system I'm supposed to be in. So I'm going to kind of wipe the slate clean and go ahead and take this back to Latin lawn, because we know the data's on Earth, right? We know that. So let's take it back to Earth and just wipe the slate clean. Once it's back into just strictly NAD 83 or NAD 27 or WGS 84, no other variants. Excuse me, no other variants whatsoever. Keep it simple. Once it's in NAD 83, as it is in this example, then you run the project tool to get it to the rest of the way. So let's say, for example, I have some DNR data. I screwed it up somehow, it doesn't matter. I go to my Define Projection tool, I go NAD 83. Boom, it takes me back to Latin lawn, kind of wipes away everything, all of the two-dimensional garbage that was in there. And now I use the project tool and go the rest of the way. So then the project tool would be Harn, Wisconsin, or NAD 83 Harn, Wisconsin Transverse Mercator. And it'll give me the option to use a transformation. But that is in the project tool. You'll notice, again, let me explain, there is no output to this tool. Do not run this tool unless if you have a copy of the data. Always keep the original just in case something goes haywire. All right. It sounds like overkill, but making a copy is right click copy, right click paste. It takes 2 seconds. Run the tool, get it back to its very basic form, NAD83, NAD27, or WGS84. No other variants, none whatsoever. Just those three. Then use the project tool to create a new output, and then you'll be good to go. That's what took me about 5 years to figure out. Okay. I've done it this way since like 2008, right? And it has never failed me. Now, there are people that'll tell you that you can actually put a projection, a two-dimensional projection in the box here. I've tried doing that a couple times, and unless if you absolutely know that's the correct projection, I don't recommend it. Please don't do that. If you follow my methodology, it takes about a minute longer and you will get the right answer every single time. All right. So that's one of the things about this chapter that again, a huge part of GIS is coordinate systems, figuring them out, fixing them, and making sure all of your data is consistent. And the define projection tool is a great way to kind of wipe that slate clean and make sure that you're starting from a clean piece of data and then going from there. Now, you don't have to do that for every piece of data you own, but if you have issues with one where your data sets aren't lining up, then you have to. The other time you have to use this particular tool is if your data set says unknown. Now, let me give you an example of this. So the methodology, I use earthquake data. I do earthquake stuff sometimes. And a lot of times when you bring in earthquake data, it's in a comma separated file or like an Excel spreadsheet kind of thing. When you bring that into GIS, the program has no idea what to do with it. Even though it's in Latin line, you're telling it's Latin line, it still doesn't know where on earth it is. So once I get it into GIS, and you'll do this in the tutorial, all right. So once I get it into GIS, I do what's called display XY. Again, you'll do this in the tutorial. It's super easy. Then I once I have that, I export it, okay, to make it a permanent feature. I use the define project tool to just do NAD83. Now my data will show up on any map. And then if I know I'm using a particular two-dimensional coordinate system, I can take that and project it with the project tool. So that's a three-step process for bringing in unknown data, completely unknown data. You bring it in, you display it, you define the projection, which is just the GCS portion, and then you project it. 1, 2, 3. And I've done this so many times. Once you do it a couple times, it's super easy. It's just you have to know that sort of three-part step. But I'm going to repeat myself one more time. Make a copy before you run this tool, and nothing should ever be in this box other than NAD83, NAD27, or WGS84, depending on which coordinate system you decide to use. Okay, it's hugely important and will save you a ton of frustration because coordinate system issues can be somewhat frustrating if you don't know what you're doing. If you run into this issue, come back to this slide and hopefully it'll help. So here's another example of why you would use the define projection tool. So here you can see the data is clearly in Latin Lon, but it's labeled in meters. Okay, so something is obviously wrong there, mislabeled. So how do we fix that? Well, if you listen to the prior slide, you should already know that if something's wrong, take it back to its basic form, wipe the slate clean, use and go back to just the GCS using the define project tool. And that, so make a copy first, always make a copy. It's not hard, it's not a big deal. And then here you go, there's GCS 83. It'll relabel the data. So now your data would be in Latin Lon, true Latin Lon with the correct labels, and then you could use the project tool to go from there. So one of the things that confused the bejesus out of me when I was first learning GIS was how to fix this stuff. There was no like I didn't understand the difference between these two tools. It wasn't until I got the textbook, the original version of the textbook I started using, and she had both of these on in the book, and all of a sudden the proverbial light bulb went off. This is a very, very important slide. You know, the define projection tool, it should only be used when the coordinate system is missing or incorrect. It, the biggest thing is this. If you don't see an output, you're probably using the wrong tool. The define projection tool should only be used like 1% of the time. 99% of the time, you're going to use the project tool, okay? Because most of the time, you're going to get data in lat/lon or maybe a two-dimensional coordinate system, and you want to change it. And that's fine. You can do that. That's perfectly legitimate. In fact, you should do that. If you have a coordinate system in mind for your entire project, that's exactly what you should do. But the big thing with this is that it creates a new data set. So you're not messing with the original. You're getting a new data set. So if you happen to screw something up, you delete it and rerun the tool, no harm, no foul. But with the define projection tool, always make sure you keep make a copy of the original data before you use that tool. So we've come to the end of chapter 4 in coordinate systems. I hope you can understand the importance of what this does. And you're going to have to do some of this stuff if for your projects, obviously, because I require all your data in the same projection. If you're downloading earthquake data, or if you're downloading, I think precipitation data is the same way. You're going to have to know that 3-step process where you bring in your spreadsheet. You have to right click on it. You go display XY data. You tell it which column has the longitude, which column has the latitude. Then it creates sort of a temporary file, which are called events. And then you export those. And you can export those by themselves or in the data frames properties. Use the idea is you have to make sure you keep it in lat/lon, whether it be the define projection tool or the data frame properties, and then project it to your two-dimensional planar system. This stuff becomes second nature. It's not hard to do. You just have to know the steps. Okay, none of it's hard. The tools make this super easy. You just have to know the steps ahead of time. Now, the other thing I did not mention is it's really, if you go back to that cardinal rule of GIS I mentioned, where the first piece of data you add is it assumes that coordinate system. So when I'm doing things like bringing in earthquake data, okay, I already know that there's no coordinate system for that whatsoever. So what I do and what you should do always is when you have unknown or you're trying to fix coordinate systems, do it in a blank in a project. Don't have any other data on your map because the program's trying to project it on the fly in the background. You don't want to do that. You want to handle those data sets all by themselves, fix them, then bring them into your map. Okay? Do that separately from your project, whatever map you're working on. That's a huge, huge thing. It takes only a couple of minutes. Maps are a dime a dozen. You don't have to save every map you ever open. So when I'm doing bringing in earthquake data, I create a blank project. I bring it in. I display it. I export it to make it permanent. I define it, and then I project it. And I do all of that without ever opening the actual map I'm working on. You do that separately. And it makes life a lot easier than trying to throw everything about the kitchen sink on the same map, forgetting what coordinate system you're in, all of this stuff. That becomes a real headache. So when you have trouble spots with coordinate systems, or if you have unknown stuff that you're bringing in like earthquakes or precip data, do that separately. It's not a big deal. It takes no time at all. All right, that's the end of chapter 4. All right, so in chapter 5, chapters 5 and 6 are reorganized from previous versions. So the first one is going to be managing vector data of chapter 5. A lot of the aspects of that particular chapter were spread out through other chapters, so it's a bit new for me. But I like the way she organized this particular chapter. So we'll start looking at what you can do with points, lines, and polygons. That'll be in chapter 5. So stay tuned and take care.